So the big idea that we'll be using in implicit differentiation is that y is still a function of x, even though it doesn't have a nice formula involving x all by itself. Before we do any of that, let's remind ourselves, what is the derivative of 7x with respect to x? Well, you'd probably just say, oh, it's 7, right? Could we also write it 7 times, so that's d dx of 7, which is 7 is a constant multiplier, so we can just kind of ignore it. Sorry, it's d dx kind of moved in, so we can say it's dx over dx. So you could say it's 7 times 1. What's d dx of 7 times pi? Well, if we try the same thing, we're going to get 7 times 0 because pi is a constant with respect to x. And then here's the new part. What's d dx of 7y rather than 7x? Think about that. Well, 7 is a constant multiplier, and then we're going to say it's dy over dx, which is just in some sense another name for y prime, right? So this is the kind of stuff we have to keep in mind. We can't just say d dx of 7y is just 7. It's 7 times dy dx. If we had asked what's d dy of 7y, well, that's the same thing as this, and it's just 7. You could say it's 7 dy over dy, which is just 1. So the derivative of an expression involving y will involve the chain rule because y is a function of x. So the derivative with respect to x of a function will be the derivative with respect to y of the function times dy over dx. And this is where we're using that dy over dx notation that we mentioned way back when we first said notation for derivatives, but we hadn't been using it until now, but now it's really handy. So notice that that's not an x there. We went from d dx to d dy of something times dy over dx. And remember way back when we were talking about the chain rule, not so long ago, we said another way to write the chain rule is dy over du times du over dx, and it's kind of like the du's cancel, and you get dy over dx. So that's the basic tool we're going to be using here for implicit differentiation, saying d dx equals d dy of something times dy dx. So we have this new concept of taking the derivative of something with respect to some other variable, and so far it's all been the same. It's all dy dx or dy dt, but now we have to think about what that means more. So here's an applied example. Suppose the airplane takes data as it leaves an airport. So for every time block that goes by, it's recording its x position in kilometers, its y position in kilometers, its z position in kilometers, that's altitude, how high up it is above the runway from where it took off, like the external temperature, how much fuel it has on board in kilograms. And if you ask how fast is the airplane going up, you could answer that two ways. You could say, what's its vertical speed in kilometers per minute, its climb rate? How would you calculate that based on the data you have in this table so far? Well, you'd probably use a difference quotient, and you could say its vertical speed is like 0.03 minus 0 divided by how many minutes have gone by, which is 0.2 minus 0. I didn't check that these are reasonable speeds for an airplane, but whatever. But you could also ask how fast is it going up per kilometer that it goes forward, which is more like the angle of the plane, not literally in degrees, but kind of the slope of the flight path. And for that, you'd have to say, well, how far up did it go? Well, we already did that. 0.03 minus 0 divided by how far forward did it go. So now I'm using numbers from this column rather than that column. So it would be 0.05 minus 0. So is the vertical speed in kilometers per minute equal to the vertical speed in kilometers up per kilometer you go forward? Well, no, they're even in different units. So we could say here we're taking the derivative of altitude with respect to time versus with respect to forward distance, assuming it's just flying mainly in the x direction. You can talk about this for other variables too, like how fast is it using fuel? You might want to know that in how much per unit time, or how much per unit distance it goes forward. Each of those are useful in its own way, but they're different. And this is the derivative of fuel with respect to time. This is the derivative of fuel with respect to forward distance.